Hello, my name is Bassel Mabsout, and I'm a PhD student in the Cyber-Physical Systems Laboratory in Boston University. The Cyber-Physical Systems Lab really works on systems problems, so architecture and all of these kinds of things, but I am focused on control. And specifically, I am focused on how you can use reinforcement learning and learning methods, combine them with methods for achieving specification for these kinds of problems and getting the robots to behave in the way we intend. So in this talk, I'll be focused a little bit on how I came to the journey to reach that kind of specification. So inside the slides. Okay. So first I'll start off by mentioning what is a control system. What is this thing that we're controlling to begin with? I'll mention what a dynamical system is and what a controller is. A dynamical system is represented usually by an actuator, a process, and sensor readings. In general, it's some sort of physical system where you have some states that evolve over time. So imagine a river, for example, you have the water moving over time. Or if you have a robot, how it moves in space and time, that's also a dynamical system. And because we're worried about control systems in this case, and specifically robots, you would have inside of the dynamical system, you'd have actuators. So imagine, for example, a robot arm that's supposed to like unscrew a light bulb. Then the actuators would be the different motors on the robot arm. You would produce commands to control these motors, and the process that happens is the physical process that lets the arm move. You would get sensor readings, and those readings we call observations, and then you'd use those observations to further produce commands. And this is what the controller is. The controller is this thing that takes observations and produces commands. Then you have this kind of loop, and this is what is called a control loop, where there's this interaction between a dynamic system and a controller, such that you try to achieve a certain state with your system. So with the arm trying to reach the light bulb, the goal is to reach that light bulb, and your controller is supposed to choose commands such that this dynamical system behaves in a way we want it to behave. In classical control, the idea is how we can find such controllers, how we can find a controller that achieves this goal that we want to achieve. The goal is usually called a set point. So our arm reaching the light bulb, the set point is the light bulb. Where the arm is right now is its current state. And what is very commonly used to do low-level control is what is known as the PID controller. And the PID controller is divided into a proportional, integrative, and derivative part. The idea is simple. You have the set point where you want to reach, and the observation representing where you are, and this error term that you want to reduce. And the proportional part really proportionally applies some kind of force to reduce this error, proportional to the error. And the derivative part represents applying some force with respect to the change in error, and the integrative part for the sum of error. The details don't really matter, but the reason why I'm mentioning this controller is because it will be used in the next works that we will represent. And at the same time, this is the most widely used controller by far. Your amplifier, the one that's amplifying the sound on your laptop right now, is using a PID controller in hardware. The planes that you've flown in are using multiple different PID controllers to control the attitude of the plane, which means the angles of the plane. The elevator stops at certain places because it's using this PID controller to do this. So it's really used everywhere, but it has its limitations because it's so simple, because it's just these three terms that we're applying everywhere. It doesn't mean it can control all kinds of robots. You cannot use a PID controller, for example, to control a walking robot, because you need to plan how each joint needs to go so that the robot doesn't fall. And your goal isn't just to minimize some error, it's to not fall, for example. This is a high-level goal. It also cannot handle high-dimensional observation. You cannot expect a PID controller to be fed an image and produce a command that will achieve the goal that you want to achieve. And it fails at controlling systems with high performance in some cases. And I'll get to an example of such system. Okay, so one response to this is what the people have been doing in reinforcement learning. In reinforcement learning, the benefits are that you can control you can hit those limitations that we've had in the PID controller. And indeed, these limitations are the case in many classical control theory algorithms. It's not just the PID controller. But in reinforcement learning, we can handle high-dimensional observations. It's a black box data-driven method, which means we can literally try finding controllers in reality directly, rather than having to model how reality works before producing a good controller. We can also cheaply and quickly iterate on robot design in some kind of simulation, producing controllers that achieve this high-level goal that we want. So for a walking robot, you can imagine the high-level goal is reach the table or something like that, where you could add a leg, for example, and the high-level goal remains the same. But for classical control theory, you will need to now understand how this extra leg modifies the physics so that you can try to achieve control on this kind of system. The cons are also very large with respect to reinforcement learning. The biggest one is that you have no guarantees, and you don't know whether this found policy is a controller, this found controller or policy is one that will achieve the behavior that you intended to. We don't know whether it will work in reality if it worked in simulation, and it can be fairly sample inefficient. It's data driven, but you need a lot of data in order to get the controllers that are good in a lot of circumstances. Here, for example, we have a controller for a robot arm that solves the Rubik's Cube. Well, this is a person earlier. We have this robot that is trying to solve the Rubik's Cube via a dexterous manipulation task. And we are far from doing this, from solving this problem in classical control theory, but with reinforcement learning, it can be done. Over here, we have a bunch of cells that are being controlled by light. This is a self-drifting car that is learning to follow this course as efficiently as possible. It's often used in industry because it's cheaper to produce controllers on these kinds of problems than it is to solve the actual classical control theory problem properly. Okay, so what does reinforcement learning rely on, mathematically speaking? It relies on the idea of a Markov decision process. And the Markov decision process is essentially this three tuple of things, technically four tuple of things, where you have a state space. So you can imagine, for example, a chessboard. Your state space would be the space of possible legal configurations of that chessboard. Your action space, which can represent the possible moves you can take, starting from any chessboard position, and a transition function such that when you're taking this board configuration and you're taking an action, you are now going into a new board configuration. And what is known as a policy, which is what your controller does. So given a board position, you want to produce an action, a board move, so that you can try to achieve some goal. This is the same thing as a controller. You can even think of computers as deterministic Markov decision processes, where the state space can be whatever's in memory, and your transition function is what program you're running, for example. There is this one key thing, which is the Markov memoryless property that makes it a Markov decision process, and it's that this function is a pure function. So given an exact state and an exact action, you will always produce the same distribution of states, independent of what states you've previously passed through. So walking through a Markov decision process works like this. You have a current state. Your policy produces an action. This goes into the transition function along with the state, producing a new state. And you have this loop. And it looks a lot like the control loop we had earlier. There's an extra thing here, which is the distribution over states. And this allows for stochastic transition functions. And this Markov decision process is not necessarily deterministic. It can also be stochastic. And for real robots, we care about this because you might have disturbances in how this thing works. So for a quadrotor, for example, that's trying to fly, you might get wind that's a disturbance. Or a walking robot, you might get somebody that pushes the robot, if this is what they like to do. Some people like to do that. And the point is that we can use stochastic systems here, and our sensors can also produce some random noise included in there, and we can still produce controllers with respect to those systems. Okay. And in reinforcement learning, what we're trying to find are policy SPI, which are our controllers, such that they maximize a notion of a reward. So we have a reward function. When given a state and an action, we produce some real value. This is what we use as people trying to engineer the controllers that need to get output as a specification. It's what the policy must do in order to get good points. And what you define as good points is this reward function. Usually you want to define this reward function in a way that tries to really represent what you intend. In programming languages, that could be your specification. And here it's just a reward function. There is another parallel here. In programming languages, you can know that the specification is satisfied. In a reward, you're just maximizing this number. So you don't know when you actually have a robot that is really doing what you intend. So those are some kinds of pros and cons in this by representing things in this manner. The thing that's getting maximized is the sum of rewards over the states that have been that will be observed. So you're not maximizing that reward over the next step. So you're not trying to find a policy that is maximizing the reward that you will immediately get. You're not greedy. You are instead trying to find to maximize the sum of the rewards, so that maybe if I skip a coin now, if I'm playing Mario, I can get 1,000 coins later. So that's what your policy needs to do. Okay. And I'll talk about a little bit why we're talking about just classical control theory and racing and reinforcement learning and all of that. And it started actually with a project that a student in our cyber physical systems group did. His name is Will Cook. And he thought that classical control theory is not, at least the PID controllers that people use in things like this drone, is not, doesn't achieve the performance that he believes is possible. So he decided, okay, let's try to improve that performance. And in doing so, he focused on this racing drone case. Trying to achieve high performance on these drones is not an easy task, because these drones have a very constrained embedded system due to the fact that you're trying to minimize size, weight, and power. Because you want the racing drones to fly faster for longer. You want to minimize those, which means you cannot really put a lot of, you do not get the ability to have a lot of processing power in there, which constrains what kind of control algorithms you can run. What I mean by attitude control is allowing the drone to rotate about its central axis. So it's rotational control. You are trying to control the rotational velocity of the drone via some kind of analog stick. And that would be the person doing the racing. They're trying to get the drone to reach some certain angles so that they can avoid some obstacles. So it's still considered a low-level control task, and this is where PID control is used more often. And indeed, on any drone you'll find, it'll be a PID controller that's running on the stick. The processor on this is a Cortex M7, and we only have 216 megahertz of processing speed to work with. So it's not like we can put a huge neural network on here, but we can run a 32 by 32 or a 64 by 64 neural network at around at near 1,000 hertz, 900 something hertz, while a PID controller can run at 1,000, at 4,000 hertz. Some people really maximize how the frequency of this control loop to try to maximize the performance of these systems. Okay, so what Will did was the starting point, which is the starting point of this journey of the talk here. And he built what is known as Neuroflight. He created a simulation where there's a drone model, and he used a reinforcement learning algorithm to try to produce a controller that is then compiled into an existing open source firmware called Betaflight. And then he would fly this drone in real life, where this neural network gets invoked with whatever sensor readings we get, and the inputs that the set points that the user has with respect to their control inputs. So let's say a racer is trying to get the drone to fly in a certain way. We get the signal on the drone, and the neural network controller is trying to follow those commands, producing motor signals to the four. We have the 4 blades here, so we have 4 motors. So it produces 4 outputs, telling how the motors need to, where the motors need to, how much power the motor needs to pull in order to try to achieve this controller, this control objective. It's not an easy control objective because we have 4 motors and we have 6 axes we want to control the quadrotor on. We have X, Y, and Z over the Euclidean space. And we also have roll, pitch, and yaw for the angular velocities we want this thing to reach. So we have 6 channels of control and 4 channels of actuation, which has a specific term in classical control theory, which is that it's an under-actuated system. And it's why it's kind of difficult to control it, what makes it non-linear. So there is a simulation, and this is what it looks like. I'm not showing here like a maneuver, but this thing rotates about its center. And Neuroflight, through this reinforcement learning algorithm, produced policies/controllers that are capable of achieving this goal in simulation. So here's a comparison between PID and PPO. PPO is a reinforcement learning algorithm, and we can see how PPO is capable of reaching the goal faster than PID is, at least in simulation. And we can see the control outputs for over each motor and how that looks like once that's trained. Okay, and here's an actual flight of this thing. This is this drone. And we can see the motor usage being a bit wild here. I'll get to what's going on. But the point is that this thing is controllable. I'm able to control it, and this controller trained in simulation is capable of transferring to reality and performing actual control on an actual robot. Okay, but there is a big problem. These motor outputs are all over the place. And even though in simulation it wasn't the case, in reality it is. And these are due to the fact that reality behaves a little bit differently than simulation. And those controllers trained in simulation are really tuned to do well in simulation, and they do not perform that well in reality. And it's because we really don't understand what this controller is doing. You have this reinforcement learning algorithm. It's maximizing this reward function that's trying to represent what you intend, and it's trying to do what you expect, but in a different environment. You have no guarantees, so this is what happens, at least in the case of this quadrotor controller. When we look at the Fourier transform of this, we see there's a lot of very large amplitudes on the higher frequency components, which translate to a very large usage in power. So a PID controller uses 8 amps on average in these flights, while Neuroflight uses 23 amps approximately. It does achieve a little bit better tracking the trajectory that we wanted to track, but not significantly better at a very large cost. Although in simulation, this Neuroflight controller achieves a significantly better performance. So this is the thing that motivated our work in RA+AL, and specifically how to train a quadrotor, which I'll get to. The main problems that we're seeing here are that reinforcement learning can learn to control a quadrotor, but it produces these abrasive outputs. And only 1 out of a dozen trained agents was actually even flyable. The rest were either unstable, so you try to turn them on and they do something weird, like they fly in a random direction, or they turn the motors so hot that this thing shuts down. In some cases, we've ruined a few of those motors. That's expensive and it's unsafe. So this is something that's very that can be very dangerous. And the drone has attacked me multiple times, if you're worried about it. But we have a net in the lab, so we have safety. And this is not a problem that is only one that appears in this scenario. It's actually something that has been documented in multiple papers, and it appears across different domains. People doing reinforcement learning on arm control, people doing reinforcement learning on trying to fly helicopters. It's all over the place. And why is that so? I'll get into that. And I'll get into how we solved that problem and how to train your quadrotor, which is the first paper we did in trying to attack these issues. So this is called a framework for consistently smooth and responsive flight control via reinforcement learning. I think the title could have been a bit better, but whatever. So in how to train a quadrotor, what we did was we first modified the state space to contain enough information to satisfy those Markovian assumptions, specifically the Markovian assumption of memorylessness. It wasn't the case that in Neuroflight that this was satisfied, and actually it's difficult to satisfy this property on real systems, because one thing to understand is that the gyro readings that you get, those sensor readings, they might have noise that is not independent. And in having noise that is not independent, you now depend, figuring out where you are in space depends on knowing what your previous states were. We fixed that by providing enough of the history of states into this input that there's enough information to reconstruct where the drone is so that we can actually perform proper control. And we focused a lot on this reward function. Since this reward function is supposed to represent the specification of how the robot must behave, you want this scalar to represent your intention, and it's actually difficult to do that. And I'll mention how we how it was all about composing different rewards that led to the results that I'll show. Okay, so in Neuroflight, what was the problem? The problem was mainly the way Will did reward design. He would design some rewards that where he believes represents his intention. He would train the reinforcement learning algorithm, which would produce a controller. He would look at how the controller behaved. And then if he didn't like some behavior, then he would then add something to the rewards, modify a few numbers in the rewards, and through that, slowly increasing the complexity of the word structure to try to achieve the behavior that he wants it to achieve. The reward components that he ended up with was one that penalizes maximum change in motor output, which means you don't want your motors to change very much, the output of the motor to change very much, which is the thing that we thought, the abrasive outputs. That's something that he didn't want, so he added a reward for it. It looks like this. A reward for maintaining a mean motor usage. He observed in certain cases that the policies learned do nothing. And he added a reward component that tries to reward using the motor a little bit. He had a reward/penalty for tracking error, which means how well the drone is given rewards if it's following the trajectory well, and penalties if it's not. And then he penalizes the maximum motor usage, which penalizes the motor that is using 100% of the output. What I mean here isn't really very accurate in terms of the exact equation that's being represented, but really the point is that he made all of these, he added all of these different reward components, where you can see here that some of these values are a bit crazy. These weights are, this is at 10 to the power 9. He also had a penalty for not actuating motors at all, which again is at 10 to the power 9. He arrived here not by being dumb in how he's doing the reward engineering. He did start off with a simple reward structure, one that you would expect would represent your intention. But through this experimentation procedure and through him observing that the policies does not achieve the goal he wants to achieve, he ended up with this these reward components. Instead, in RA+AS, which is how to train your quadrotor, we only have 3 different reward components. A change in motor output penalty, which just penalizes the difference in motor outputs over time. The distance from the set point penalty, this is the thing that will get the drone to follow the trajectories that we want it to follow. And a high motor usage penalty, because using the motor more means you are using more power. So even if you're not changing how you are using the motor, just having the motor spin at 5,000 RPM is using more power than having the motor spin at 2,000 RPM. And this is the reward component that penalizes this. So how were we able to simplify the reward structure to the following and get the drone to work in the way we want it to? Well, it was all about reward composition. The problem is you are trying to represent this behavior in this domain of real numbers, and you have multiple competing rewards. If you think about the goal I had here, which is really these two are representing the goal of having good power consumption, while this one is representing the goal, this one is representing the goal of following the trajectory, while these two are representing the goal of having a good power consumption. And these are competing. If you're trying to follow the trajectory very well, you might need to use the motors more, which versus doing nothing, where you consume no power. So they compete. And there's a game theoretical notion here with respect to trying to achieve what is known as a Pareto optimality, but we can set that aside for now. The point is we want to come up with this reward that represents what we mean. We want this goal to be satisfied and that goal to be satisfied. So our semantics are to satisfy both. And the problem is that when you train the policy on one goal, it behaves in the way you expect. If you train it on the power efficiency goal, it learns to do nothing. If you train it on the follow the trajectory goal, it learns to do high performance maneuvers, but at the cost of a very high power efficiency. So it knows how to follow each single goal, but how do we get it to follow both? To represent this problem, I will just show an example. Let's say we represent our goals as something we can satisfy. That's continuous value between 0 and 1. So rather than not satisfied being 0 and satisfied being 1, and there not being anything in between, you have all the range in between. It's similar to how fuzzy logic works, where you have constraints that you want to satisfy more. Like you have this kind of idea. If we have, for example, let's say our trajectory tracking is at 0.2, so we're not doing really well on trajectory tracking, while our power consumption here, y, is at 0.8, so we're doing well on power consumption. If we add them up, we get to 1.0. If we multiply them, we get 0.16. While let's change these values. So let's set x to be 0.15. Now, we reduced how well this thing follows our trajectory. So it's doing worse on following the trajectory, but better on power consumption. If we add them up, what you get is 1.05. This number is larger than that one. So essentially, we're saying this policy that produces this number is a better policy, even though we are doing worse on the component that was doing pretty badly. However, if we multiply them together, then this number goes down. And if you think about it, at the limits, it works a bit well, it works exactly how the AND function works. If you multiply 0 by any number, it's 0. So 0 and any other thing is 0, right? While if every component is 1, you'll get 1. So you're preserving these semantics. In additive composition, this is not the case. So this idea of multiplicative composition is the first thing that we decided to explore as a method for composing reward in reinforcement learning. And here's a visualization of what that looks like. We decided to use a geometric mean, which does multiplication, and then it takes an nth root. This is for technical reasons with respect to how the reward actually competes with itself over a sum of rewards over the episode, but I won't get into those details now. But the point is, if one of them is 0, then this evaluates to 0, and the only way to improve is to focus on the lower performing goal. So if you want both goals to be satisfied, it makes sense that that a better policy is one which maximizes the one that is the goal that is doing worse. Okay, so we tried it out on the problem of quadrotor control, and there's a little bit of a funny story here. The first time I tried running the RE plus AL technique on the drone, I started training, went into the shower, and came out, and I was looking at the numbers and wasn't believing what I was seeing, because the work with Neuroflight took 16 hours before sometimes producing controllers that achieve the behavior that we want, while the RE plus AL method was able to get policies learned to achieve the behavior that we want in 20 minutes. And it was extremely reproducible. Every time we ran training, we would get the same behavior. While in Neuroflight, what you would get is under different seeds, you would get completely different behavior, because this in this competition of rewards, what was happening is sometimes one wins over the other, and that throws you into a local minima of what this policy is trying to achieve, which throws it even further into this local minima, getting stuck in various different local minimas. And this is why Will ended up with this very complex reward structure. It wasn't his fault. It was really the problem of how people tend to compose these rewards together in reinforcement learning in general. There is a whole field of study in how you can try to represent your intent in rewards, and that's called reward shaping. But we're the first to structure things this way. And really the ideas that I'm thinking about are coming from how we define specification, propositional logic, and stuff like this. Okay, so here's a video of the flight just to show that this thing really does behave well. I'm showing a little bit of a few high performance maneuvers here. I should be doing a flip at some point. Okay, there you go. That's a flip. Okay, so the results speak for themselves, really. This is a PID controller's outputs versus Neuroflight versus RE plus AL. this is the same thing, the same simulation. We trained our reinforcement learning algorithm in simulation, but now in reality, it actually is robust to those changes. And this is what I meant in the title of the talk when I said robust. It means that you can change the dynamics a little bit and you still retain the same behavior in terms of the policies that you get across those transformations. The nice thing about control theory is that you can get some guarantees with respect to that. And I'll get to the type of guarantees we can even get with these kinds of methods later. That translated to massive gains in power consumption. The Neuroflight was able to produce controllers that had a power usage of around 23 amps, while RE plus AL was able to produce 5.86, and that's lower than PID. And it's also significantly higher performing than the PID controller that's tuned in reality. These the three parameters, the KP, KI, and KD in the PID controller, were tuned as best as possible in reality. So this is the best it can possibly do. Okay. These ideas of reward composition we thought were general enough to try to apply to different methods. And we tried them on these 6 different benchmark environments that people tend to use in reinforcement learning. And we tried to see if we could re-engineer the rewards to be much simpler in all of these environments and try to still achieve the behaviors that we want them to achieve. And it's indeed the case. We observed a 50%, like greater than 50% reduction in reward variance across different benchmarks. That means across these different environments, the policies that are learned do the same thing. They learn to do the same thing. And in some cases, it's actually more than 10 times lower in terms of this variance. And we even tested them on the original rewards that people did, which is this with this linear composition, and we saw it improve in performance even when it was optimized for our multiplicative rewards, which were minimally, like I just went in, saw what people are intending to do, wrote the rewards very quickly, and from many of them from the first try they would just work. Okay. So that concludes the work for the RE plus AL stuff, but we didn't stop there. The journey took us towards the next work that is called CAPS, which is Conditioning for Action Policy Smoothness. And in that work, what we wanted to do was we wanted to try to preserve the reinforcement learning environments that people already have. But sorry, do you have some question? Anybody have some question, actually? I can respond to those right now. I can't really see the chat, so I should try to. Oops. Let me see if I can.
I have one quick one. When we're talking about linear combinations of rewards, the additive version,
yeah.
One of the things that people play with a lot, I guess, is exactly what weight to put on each reward.
Yep.
What is the analog in multiplicative rewards?
Oh.
Can we emphasize one reward more in some way?
Yes, you can. You take it to the power of something. So if you want one reward to be more important than another reward, the way you do it is you, for example, say we have X and Y here, then you take X to the power 2, for example. Then that number will be smaller, right? Because it's smaller now, it holds more importance. Because it holds more importance, it's focused on more. So this is how you can tweak what is more important than the other. Yeah, and actually there is a much nicer structure here that generalizes both over the geometric mean and the linear scalarization. If you take something called the generalized mean, then both of these are an instance of the generalized mean, and we actually use that in later works, but I will not get into the details. The really nice thing is, if you work with the generalized mean, you can have an infinite space of these types of composition operators that can mean all of the range between the and the or operator. Like you can smoothly move between the and the or operator depending on how leaky you want it to be, which might make it easier for the reinforcement learning algorithm to find policies. It's not something I will get into the details of just because I just don't have the time, but I think it would be interesting for you in this case.
I had a question. If you answered this earlier, I was late. So if you answered this earlier, I'll go back and watch the recording later. But how do you incorporate exactly the user controls into like the desired behavior? Because I just imagine part of the challenge is figuring out what you want the inputs to mean. Like is it obvious that like pressing the stick forward means fly forward?
Yeah, okay. So in our case, it's not that difficult. Let me see if I can go navigate back to the reward structure. Wait, actually, I skipped it, sorry. Reward structure was after this. So, okay. In our case, the actual controller, the person's holding, it's asking. So the control input is asking for the set point that this thing needs to reach, which is, for example, please rotate around the yaw axis at 800 degrees per second, or 300 degrees per second around the y axis, around the yaw axis. So these are the things we want our robot to achieve. In this case, this input that we want to achieve is easy, right? So there's no complicated thing that you need to apply as a way to try to achieve your intent with respect to following those set points, because really you can represent it as the distance between how fast this thing is rotating around the axis that we want versus how fast we want it to, right? It's rotating at this speed, we want it to rotate at that speed. That's our error. This is the thing we want to minimize. This is the trajectory we want to follow. So really, it's not a difficult problem in that sense, at least for quadrotor control. And getting the robot to go forward, for example, and hitting and avoiding obstacles, this gets difficult because avoiding obstacles is a difficult objective. But you can always design rewards to say 1 means you are right now not hitting an obstacle, 0 means you are hitting an obstacle. Stuff like this. You will have to get into trying to figure out what that goal is, which is this goal that needs to be represented between 0 and 1, so that the sum of those goals represents your intent. It can get pretty hairy for sure. You're welcome. Okay, so let me move on to what we did in CAPS. In CAPS, the point was let people design their rewards, let people design their environments, which are those dynamical systems that are simulated usually that the reinforcement learning algorithm is running in. And we will try to modify the algorithm so that we don't get these abrasive outputs, since this is a common problem across. Sorry. Hello. Somebody say something.
You're good. You're good. Continue. Okay.
In trying to not have these abrasive outputs across multiple of these different problems that existing works has, we wanted to see whether we could force the reinforcement learning algorithm to produce policies that do achieve this behavior just by construction. And we did so by focusing on Lipschitz continuity. The idea of Lipschitz continuity is to disallow functions from growing or decaying at a rate faster than this k linear. So if I need to explain this a little bit better, I can follow this visualization, and functions that flow in the domain of where this region is red are allowed, where if they grow faster than this white region, they're disallowed. It's a constraint on the growth of these functions, and we can use this to try to represent our idea of you're not allowed to change the most outputs over time.
Just like a smaller bar. Like Loki is basically just like a smaller, like less like grand bar. That's all that bar is.
A bar? Sorry, I didn't hear that well. It's a smaller bar.
I think someone was unmuted and didn't realize it.
Oh, I see. Okay. Anyways, the way we try to represent the idea of not changing our outputs very much is via this idea of the Lipschitz continuity. And we added to the reinforcement learning algorithms that were most commonly used at the time, two optimization criteria, one for temporal smoothness and one for spatial smoothness. Essentially, we constrained the Lipschitz constant for actions, subsequent actions, and we would have some distance metric with respect to this action space that we had defined earlier, saying essentially that we're not allowed to change the actions over time very much. At the same time, we had the spatial smoothness, which meant that similar inputs to the controller would produce similar outputs. So we're constraining also the output of the neural network over the input space. So we're constraining that over the observation space and the action space. Okay, and we tried that over a few algorithms. You can see here TD3, which is very commonly used deep reinforcement learning algorithm, producing a controller for the pendulum problem. The pendulum problem tries to get this thing to stand upright. And you can see that it has abrasive outputs. There's no reason for the policy to learn something smooth, but with caps, we get just this smooth output by default. And we show that this is the case across many different existing benchmarks as well. You can, we introduce the smoothness, this measure of smoothness that allows us to measure this, how rough the signal is. And we show that we can reduce smoothness very significantly in a lot of different tasks without affecting the reward much, without affecting the reward that you'll get at the end of the day much, without touching the original reinforcement learning environments. This is opposed to asking everyone to restructure the rewards. And in Neuroflight, we tested it out, and you can see the difference. So this is the motor output that we get from Neuroflight versus the motor outputs that we get in a similar point in the flight with caps. And this is 30 amperes here versus 3.91. Here's a flight, and you can just see me going between the trees and stuff like this, just to see that just to show that this thing is controllable. Okay, and we compare the fast Fourier transforms. This is PID, this is PPO plus caps, and this is PPO is the reinforcement learning algorithm, and this is Neuroflight. We do even better than PID in terms of the high amplitude frequency components. In PID, you have this drop off just because people added a filter to the inputs, and the filter would manually try to achieve smooth outputs essentially, but this is well understood, and you cannot easily add a filter to a neural network controller, at least from the studies that we did in the paper. Okay, and this will bring me to the final work that we've, the final paper that we've submitted more recently, and this has to do with trying to achieve even better performance. In doing so, what we tried to do was adapt these agents live. So we took the reinforcement learning algorithm that was training these policies in simulation, and instead we allowed communication between the drone and a base station, and we got data from reality, and we got this reinforcement learning algorithm to adapt the policy to what we're seeing in real life. Our basically the our hypothesis was that we could achieve higher performance when this gap between simulation and reality is not there. This produced a problem, and I'll show the problem here. On the left is what would happen if you naively just apply the reinforcement learning algorithm on this problem. And here's an update where this neural network is being sent to the drone, and you'll see what happens when you do that. So the drone went in what we call it became unstable, while with our swan flight method it wasn't the case. So how did we achieve this? We achieved this by trying to satisfy the goal of having high performance both in simulation and reality. The problem presents itself in what is known as catastrophic forgetting. You have a huge amount of data. This thing actuates at 1,000 hertz. So you have 1,000 observations per second. And your reinforcement learning algorithm, what it's doing is trying to maximize this reward in that over this large amount of data where you're basically doing nothing. People, when they're flying the actual drone, most of the time it's not moving. And because of that, the set point is usually very close to where the drone is. So the reinforcement learning algorithm learns something wrong here. It learns how to follow set points that are near, but it forgets how to follow set points that are far away from it. And this is due to the fact that we have no guarantees with respect to this. There's nothing that says that it will follow our intention. Because of this, we had to include this idea of anchors, where we would need to satisfy our notion of performance both in simulation and reality. And in simulation, we get to choose the distribution of data so that high performance maneuvers are equally likely as low performance maneuvers. And we can make sure that our policy is behaving correctly over the cases where we want it to behave correctly. So combining both allowed us to reap the benefits. Here is, for example, a domain A where we want this pendulum to point to the left, where a domain B, we want the pendulum to point to the right. And a domain B with a domain A anchor, what it does is tries to satisfy both, so it points somewhere in the middle. It compromises. And this is actually the drone flying in real life and adapting while it's flying. We built out the system where we do the communication to try to update this neural network live without any hiccups. And it just works. And it's available to the research community for anybody doing adaptive control these days. We saw significant gains in power consumption after adaptation, because now we're really running in reality. So we were able to get even more power output out of this thing for a longer period of time. Like I said, the reinforcement learning provides no guarantees. I don't have enough time to show a lot of this, but the point is this agent is supposed to score a goal, while this agent is supposed to stop the ball from going into the goal, so it's the goalkeeper. But the goalkeeper can do weird things to get the other controller to never shoot the ball, or shoot the ball in a very bad way, and actually win more times than this controller would. And this is because it doesn't have to follow our intention. Even if your reward represents what you intend, doesn't mean the policy will learn what you intended to learn. So what I'll conclude this talk with is the work we're doing right now, which is in Certiflight. And we are trying to move beyond reinforcement learning, where you could learn a controller that you can prove will actually satisfy the goals you want them to satisfy. You can do so via actually learning a neural network which acts as a certificate, employing an SMT solver that checks whether your neural network is doing the right thing over all of the space where you want it to do the right thing, and adding counterexamples to your data set where this acts as a proof. Okay, so this is where I'll end the talk. And there's of course much more I can mention, but Yeah. We're moving towards both learning and certification at the same time.
Are there any more questions for Bassel? Okay. Well, thank you, everyone. Thank you, Bassel. That was great, actually. It's very interesting. And we appreciate you taking the time to share all this with us, and I'll get back to you.